Hello everyone, welcome to my presentation. I am Mahdi Sedaghat, and the title of this presentation is Cross-Domain Attribute-Based Access Control Encryption as a joint work with Bart Preneel. In this presentation, first of all, I start with the introduction and main applications for such systems, and then I explain the model and the architecture of the construction and the challenges and security requirements. And then I discuss about the generic construction that we propose in this paper and the main ingredients and main building blocks that we use in this construction, including the structure preserving signatures, non-interactive zero-knowledge proof systems, and the randomizable ciphertext-policy attribute-based encryption schemes. After that, I discuss about an efficient instantiation for this generic construction and its performance. And then I discuss about some open problems and references later. Encryption is the process of scrambling the data, either in the symmetric way or asymmetric way. In the symmetric encryption, the group of sender and also receiver are agreed on one single secret key, and then the data owner, by taking this secret key and also the plaintext, can generate the ciphertext and transmit it over the network. This will be guaranteed that only the users who knows about that secret key can learn and find out the ciphertext, and the rest of the parties in the network can learn no information about the sensitive data. But whenever the number of the receivers is large, the key management issue will be problematic in the symmetric encryption, and we use different techniques like broadcast encryption. The data owner, Alice, in this example, by taking the public key of some specific and some determined and authorized group of receivers, encrypt the data, and then transmit the ciphertext over the network. Only the users that they are authorized by the data owner can learn about the plaintext, and the rest of the parties can learn nothing about it, even if they are colluding with each other by combining their secret keys in a malicious way. Based on the application, assume Alice is working in some top clearance companies like cryptocurrency wallets or other companies that they are handling some secret information. Alice is allowed to work on some sensitive data locally, but she is not allowed to transmit it over the network. Alice can do that by encrypting the data and transmitting the ciphertext to some specific parties over the network, but this will be problematic for the company. Based on the Bell and Lapadula seminal work, we should care about not only who can learn and read the plaintext, but also we should care about who can send and write over the network as well. In 2016, Damgard, Haag, and Orlandi proposed access control encryption to answer this question as a cryptographical way, such that only authorized users can communicate based on some fixed predicate function. As we already discussed in the previous slides, the standard encryption is unable to cover both of these requirements for us, because in the standard encryption, the data owner or the sender has no limitation for transmitting and broadcasting the ciphertext over the network. Access control encryption considers an entity in the middle that is honest but curious as the sanitizer, and the sender and the receiver can transmit and also communicate with each other based on a predicate function. This predicate function is fixed in the setup phase, and if the value and the result of this predicate function for two specific parties be equal 1, then they are allowed to communicate and the sanitizer deliver the ciphertext to the receiver. Otherwise, this will be banned by the sanitizer. There exist 4 main entities, including the key generator center, senders, receivers, and also the sanitizer. The key generator center is responsible for generating the encryption key and also the decryption key. The group of senders who knows about the plaintext, by taking the encryption keys, generate ciphertexts and transmit it to the sanitizer. The sanitizer, by taking the ciphertext, checks the credentials, and if they are following fixed and predetermined predicate function, then the sanitizer runs the sanitization phase and generate the sanitized ciphertext and deliver it to the receiver. And if the predicate function does not allow the sender for having such a communication link between sender and also the receiver, then the sanitizer will ban the request. But in this paper, we are following a different approach for the key generation center. Instead of having one single entity, we have two distinct entities, including the sender authority and the receiver authority, that each of them are responsible for encryption key and decryption key completely independent. That is proposed by Wang and Chow at IEEE SMP this year. In the access control encryption in general, we care about two security requirements, including no read rule and also no write rule, that we will discuss them in the next slide. It is important to mention that the sanitizer in these constructions is honest but curious to know about the secret information and the plain text, and also the identity of the senders and the receivers. In the no read rule, the parties and the user except the data owner are trying to learn about the information. Otherwise, if they are not the authorized user in the system, they are trying to find some meaningful information from the ciphertext. In the no write rule, the group of senders and the receivers are dishonest, and only the sanitizer is honest. And the senders and the receivers are trying to fool the sanitizer to accept some unauthorized communication link over the network, such that the predicate function is equal 0, while the sanitizer is transmitting and delivering the ciphertext to the receiver. The existing works are including the Damgard et al. That is proposed at DCC 2016, that is that the predicate function is any identity-based constructions, such that the predicate function, and it means the predicate function takes as the inputs the identity of the senders and the receivers. This can be built based on the cross-domain that we already discussed in the previous slides, but in the standard assumption that the construction that is based on the standard assumption has a exponentially large ciphertext, such that the encryption key size is also growing linearly with the maximum number of receivers that any sender is allowed to communicate with them. They improved the size of the ciphertext, but in the non-standard way, that is based on the indistinguishable obfuscation techniques. And in the another work by Fox-Power et al. At PKC 2017, they are considering a restricted identity-based predicate function that the size of the ciphertext is linear and the rest of the parameters are constant, and it is based on the standard assumption. But as we discussed already, this only covers some restricted class of predicate functions. Kim and Wu consider some fine-grained approach for the access control encryption by taking the functional encryption and also some signature schemes. But the size of the ciphertext, as you can see, is polynomially large, and also it is not compatible with the cross-domain approach. Recently, Wang and Chow consider general and non-restricted ID-based ACE construction that it also satisfies the cross-domain approach, but as you can see, the size of the decryption key is growing linearly with the maximum number of senders that any receiver can receive a message from. In this work, we are going to make it more general in the case of predicate function, to instead of having the identity of the users as the input for the predicate function, we are making it more general as the approach of attribute-based predicate functions. As you can see, our construction is also can be a cross-domain access control encryption, and the size of the ciphertext is constant. Likewise, the Wang and Zhou construction, the sanitizer in our scheme needs no key, and we call it as a keyless ACE constructions. In this paper, we propose a generic construction for attribute-based access control encryption, or to be more accurate, is cross-domain attribute-based access control encryption. As we already discussed, we have 5 different entities, including the sender authority, receiver authority, senders, and also the receivers, and also sanitizer. We use randomizable ciphertext policy attribute-based encryption in the receiver authority side to generate the decryption key for the group of receivers. And also the sender authority runs the structure preserving signature setup and also non-interactive zero knowledge proof system to generate the encryption key for the group of senders. The sender who aims to have a communication link with some specific group of receivers run the randomizable ciphertext policy attribute-based encryption algorithm and then generate the ciphertext, and also randomize the structure preserving signature that is provided by the sender authority for her. And finally, she runs the non-interactive zero knowledge proof algorithm and then transmit all this data to the sanitizer. The sanitizer run the SPS verification algorithm to make sure that the sender is satisfied some predicates and information, and then run the NIZIC verification algorithm. And if both of them satisfied, then the sanitizer run the RCP-ABE randomization algorithm and then provide the sanitized ciphertext to some specific repository in the system. And finally, the receiver, by getting this repository, if the predicate function allowed to him, can decrypt the data and learn the plain text by running the decryption algorithm. Before going to the efficient instantiation, we explain how ciphertext policy attribute-based encryption schemes as one of our main building blocks work. Attribute-based encryption schemes in general have 4 main phases, including the setup phase, that the key generator center generates the set of master secret keys and also the public parameters, such that generates the public parameter and broadcasts it over the network the public parameters and keeps secret the master secret keys. In the key generation phase, based on the attributes of the user in the network, the key generator center, by taking the attribute of the users and also the master secret key, generates the decryption key for Bob and Carol in this example. In the encryption phase, the data owner and Alice takes specific policy based on some specific attributes in the network and also the public parameters and encrypt the data based on this policy and then broadcast it over the network. In the decryption phase, if the users satisfy this policy, then they can encrypt the data. For example, Bob, who has access to attribute 2 and also attribute 1, and since this specific policy allows him to learn the data and information, then can decrypt and learn and blind out the ciphertext to learn the plaintext. But if the party is not satisfying the policy, then learns no information about the plaintext and everything will be hidden. Our second main building block is structure preserving signature schemes. They are exactly the same as the standard signature schemes, except some extra requirements. In the pairing group setting, the communication and also the signature should only consist the elements in the base group. And also for the verification of the signature, we are allowed to some generic group operations, including the multiplication, membership testing, and pairing. This construction should avoid structure destroying operation like hash function and some other primitives that they are outside these requirements. The main application for structure preserving signature is they are cross-Sahai proof system friendly and they are easy to be combined with other primitives. And it is our main motivation for taking them into account. Zero-knowledge proof systems, as a strong cryptographical primitive, allows the prover to convince the verifier about the validity of some statement without revealing any extra information about it. This can be done either in the random oracle model and by using the Fiat-Chemie heuristic or in the common reference string model. In this paper, we are using the Fiat-Chemie heuristic and Schnorr proof of knowledge to use and also take the non-interactive zero-knowledge security requirements into account. As we already discussed, we can build a generic construction for a cross-domain attribute-based access control encryption by taking three main building blocks. In this slide, I will explain a little bit about the instantiation that we propose in the paper by taking and also proposing a fully constant randomizable CPAB scheme, or we can take it the water CPAB scheme as the one of the main building blocks and the construction. In this paper, we are using the Abe et al.'s construction and also Schnorr proof of knowledge. As we already discussed, the sender should run the encryption phase for the randomizable CPABE and also then randomize the signature that is generated in the SPS setting and also run the non-interactive zero-knowledge proof algorithm to hide some specific hidden parts of the data. And then transmit the ciphertext and this auxiliary data to sanitizer, and the sanitizer, after checking and convincing about the validity of this part of information, then generate the sanitized ciphertext and transmit it to the repository that is available to the group of receivers. And finally, if the predicate function allows the receiver for getting and obtaining the plaintext, then he can run the decryption algorithm to obtain and learn the plaintext. We have implemented our efficient instantiation on Charm Crypto framework. And we are comparing our construction with Waters' ACE variation and also Wang and Zhou ACE construction that is proposed at IEEE SMP this year. As you can see, we have achieved a constant complexity for encryption key size, for decryption key size, and also ciphertext size. As you can see, we achieve also encryption time and decryption time as a constant value, and it is slightly better than the Wang and Zhou ACE construction. Although their scheme is identity based and our construction is attribute based, that is more general approach than the identity based. Still, there are some open problems. One of them is how we can improve the receiver anonymity. As we already discussed in the previous slides, the sanitizer is curious to know about the identity of the sender and the receiver. Although in this paper we are following a full version of anonymity for the group of senders, we are following a weak notion for the receiver. And one of the open problems for us is how we can improve this receiver anonymity while still we have the same performance. Another open problem is that how we can build a universal CPABE, because it is one of the important main ingredient for our generic construction, and if we have a more universal in the policy side for CPABE or randomizable CPABE construction with the same performance, then we can build an efficient and more universal ACE construction as well. Another open problem is how we can achieve the same security requirements but with different methods and with different and cryptographical primitives. Another interesting open problem is how we can decrease the third model or eliminate the needed sanitizer in the ACE constructions in general. Here there are the list of the references that we use in this presentation, and thank you for your attention.